First of all, congratulations, most of you, for making it out to this meeting. So last meeting, we talked about linear regression, and we did a project where you guys had a chance to take a data set, try to compute the linear regression, and try to do some coding. So today, we're going to do a quick review of regression and go into some different types of classification. So the three main parts that we're going to go over today is logistic regression, support vector machines, and decision trees. So these are very, very good methods that we use every day to either predict, basically create a predictive model so that we can take in data and then predict output, and then also classify and distinguish different parts or clusters of data. So the first thing we're going to cover is logistic regression. So before we go into this, can anyone give me a guess, or if you know what it is, can anybody take a guess of what logistic regression is?
Yeah, I can take a shot at it. So it's similar to linear regression, except it tries to fit a set of data points to a logistic curve instead of just a linear curve.
Good, good. And I guess going off of that, so compared to linear regression, what type of output do you usually get from a logistic regression?
Discrete.
Mm-hmm.
It's binary classification.
Good. Okay, that was good. So what is logistic regression? So like they said, it's similar to linear regression, but it's used for classification. So on the right, so that's what our typical plot or graph looks like for a logistic regression. And if you guys look on the graph, if you look at the y values or the y-axis, our values range from 0 to 1. So this is one of the reasons why we do call it binary classification. And the values that go from 0 to 1, basically for any given x value in this regression, it's gonna give you some value between 0 and 1. So it's going to give you the probability of a certain event. And so the graph or the line is called the sigmoid function. So the range is 0 to 1. So that's, again, we get the word binary from. So it uses this function to output. So for example, for 0, if the prediction value is less than 0.5, for example, on the graph on the right, if your x value is -2, -4, anywhere where the prediction value is less than 0.5, you're going to get an output of 0. And then vice versa, if it's greater than 0.5, it's going to be 1. So here we have a logistic regression in Scikit Learn, however you pronounce that. Do any of you know about or have used the Scikit Learn before?
Yeah.
Yeah, I've used it before.
Yep.
Good. Any of you, it's your first time hearing about this?
Yeah.
Okay, so Scikit Learn, so it's basically it's a software machine learning library for Python. So the main reasons why we use it a lot in data science, is it features different types of classification, regression, and clustering algorithms, including support vector machines. So basically, I assume, do you know what a library is for like languages?
Yeah.
Okay. Yeah, so basically it's the specific library that we can access that kind of helps us, and we can use to kind of use pre-built functions and pre-built methods. So we're not going to go too in depth into the actual code, but here's an example of how you would basically write out logistic regression using this library. So as you can see, I don't know if you guys ever try to write out an algorithm, or try to write out not really an efficient program, but kind of try to brute force write out a function that calculates logistic regression. If you try to brute force it and not use the library, you're gonna have a lot more lines of code. You're gonna utilize more memory, and the function's it's gonna take a lot more time to give you the output that you need. On top of that, you're just more likely to make a mistake, because if you brute force it, you're likely to use different loops and stuff, and so if you're not careful, you can get more mistakes. So for example, here, as you can see, by using the library, we can be pretty efficient in writing this. And so for those of you that have not used Scikit Learn before, or are new to writing or using logistic regression, it's really easy. Just if you literally just Google Scikit Learn, and then let's say, for example, logistic regression, it'll give you the first page of the Scikit Learn website. There's plenty of examples, and it explains the different methods, the different parameters, what it takes in, and then also, for example, the ranges, or the bounds and the exceptions for the different parameters. For example, on the slide before, whenever we introduced this, we talked about the range of how it had to be between 0 and 1. And so, all right, so now we're gonna move on to support vector machines. Have any of you heard about these before?
Yeah.
I've heard of them.
Okay, anybody want to give a try and try to define them?
So that's where, if I remember correctly, there's some kind of line or border that helps classify stuff, and then from what I remember, you have vectors pretty much like shooting off from that border visually to help classify in some way.
Sweet. So everything you said was correct. The only thing I would say is that in general, whenever we talk about different predictive models, the first thing you want to outline is what type of data you typically work with or plot. For example, everything you said was correct in terms of vectors and everything. But if I was somebody that had no idea about data science, statistics, or anything, right? The first thing you want to tell me is what data I bring in, what I do to that data, and then what I output.
Okay, so then you're going to be putting in continuous data, not discrete. And then I guess what you do to the data is you compare it to some kind of metric, and then the output is some kind of classification.
Good. All right, so for example here, what can be done to classify the blue squares from the black dots? Gregory kind of gave the answer to this.
Just draw a line between them.
And so if you had to pick drawing a line between them, I mean, there's different ways you could do that, right? I could draw like like a curved line. I could draw a line straight down, a line slanted. Are any of those wrong answers?
Well, I would, for my line, wouldn't you want to go from the origin out so you can like mess with input values?
Yeah,
Mm.
so for this function, for this example, it's like, yeah, that would be the perfectly logical line to draw. But in general, whenever we're differentiating different groups of like dots, is that we can have right here, we have two groups, right? I mean, it's pretty logical that they're two different groups, but sometimes we can have more than two groups. And so there's no limit of, well, it has to be a linear equation or it has to start from the origin. Those, at the end of the day, we want to make it as easy as possible for us, right? We don't want to, for example, this one, there's no need to make a very complicated curve to separate these. But what you want to do, depending on each case, is you want to clearly try to decipher how you want to separate different points, and then you make the accommodating line that would do so. So linearly separable data. So a 2D line can be drawn between the data sets. So good, you guys got that. If you look here, it doesn't necessarily have to start at the origin. At the end of the day, the main purpose is you don't really care too much about where the line is. All you care is that it achieves the goal of separating your groups of data. And here we have an example of non-linearly separable data. So if you look at this data set now, so clearly I have two different color points, which are really in two separate areas. Can anybody give me a quick answer of maybe what type of line or function I could separate these two groups? All right, so basically the data groups, they make two rings. And clearly it looks like these two rings, they have space between them. And so me logically is that I can't put a straight line there, but what I can do is I can put a line or circle function that goes around the blue one, but is inside of the red one. Like this. All right, so what is SVM? So the objective of support vector machines is to find a hyperplane in n-dimensional space to distinctly classify all the data points. So that's kind of a complicated way of saying of taking data and then just separating and classifying different groups of data. And in this case, n would be the number of features in our data set. For example, this could be variables. If we're talking about facial recognition, is that software or a computer has to distinguish different characteristics from your face. For example, your nose, your ears, your cheeks, the distance between those things. And so in the examples that we looked at before, it was pretty clear that there's maybe only two different groups of data. But what you're going to find out is lots of times the data that you work with is sometimes they're not that far apart. There's some points that are closer, and sometimes it's not exactly clear that maybe there's two groups or three groups. And sometimes you can't really distinguish whether there's multiple groups. It's just a bunch of scattered points everywhere, and there's no real patterns. So optimization. So the desired hyperplane is the one with the maximum margin. So the hyperplane is basically the area between the two groups of data that you're trying to classify. And so, like I was talking about earlier, is that you can draw different lines between the data to separate them, right? So in the first graph here on the left, there's different green lines between the two data sets. That they work is that they do separate the two types of data. But if we want to optimize it, we want to get the maximum margin. So on the right, the margin would basically be the distance between the two furthest points of the two groups of data.
So mathematically, is that kind of like a like if you only look at the furthest points of data in both pieces, is it kind of like a least squared regression line with those points?
It's very similar, but as we're gonna kind of look at later, is that it can get kind of complicated when we're dealing with multiple groups of data. Because for here, it's pretty simple in that it's a linear line, right? And so,
Yeah.
but if we were to have a curve, then try imagining that we have that straight bold line and then the dashed line also, like both of them curved, kind of like a snake. It would be kind of like moving. And on these pictures right now is that if you see, there's not that many data points, right? And so once you start dealing with large amounts of data and large amounts of overlapping data, then we can't really, it's harder for us to just picture what the optimal, or first of all, what the hyperplane is, or what the optimal one is. And so that's where we end up using functions and our computers to basically calculate that for us. But yes, good question. So what are the support vectors? So the support vectors are the data points closer to the hyperplane. So these are they're the most difficult to classify. For example, if you look at the two groups of data, so you got your ovals and then you got your rectangles, is that when you're trying to decide if a data point belongs to one group or the other, the closer it is to the middle, the harder it is to classify. For example, if you have, let's say one group is white, one group is black. So the closer something is to gray, the harder it is to classify it as closer to white or closer to black. And so here's a little illustration of on the left. So we have a pretty small margin between the furthest points. And then on the right, we have larger margins. And then the support vectors that basically allow us to kind of visualize and classify the different types of data. Okay, so we looked at what support vectors are, but why would we use them? So the most critical elements of the data set are these support vectors and the points that are not easily distinguishable to the groups. And so these points, they can change the position of the hyperplane if removed from the data set. So if we remember the graph we were just looking at, our hyperplane and our optimized hyperplane is really determined more about the points that are kind of closer to the middle or harder to pick between the two groups. And so if those groups aren't there or those data points aren't there, then it's going to drastically change what our hyperplane looks like. And furthermore, these critical elements basically lead to an optimization problem. If we didn't have those different points, then our life would be a lot easier in optimizing it. Unfortunately, life isn't easy, and specifically whenever we're going to be using support vectors and support vector machines, especially in depending on your field, like if you're working in data science or you're in general trying to make a predictive model, is that you're going to be dealing with large data sets. And typically, let's say even if it isn't a large data set, there's going to be different variables. If you guys remember n, which is the amount of dimensions, that's basically the amount or the number of features that we're trying to describe, we're trying to differentiate. And you'd be surprised as there's a lot of features, and typically the more features that we can distinguish and classify, the more accurate our model and support vector machine is. For example, so here are two easy applications that are used all the time. So the first one on the left is we actually use support vector machines, for example, facial recognition. So for example, if you have different pictures and faces, it makes it pretty easy to kind of distinguish the faces. And the perfect thing is n, in this case, would be the different features of the face. For example, the size of the eyes, how far the eyes are apart from each other, the size of the nose, where are the ears, where's the smile, like what are the colors of the hair, you know, the cheeks, the chin. And I'm sure there's plenty of more attributes of the face. And we've gotten to the point where, like, for example, Apple, their facial, or Snapchat, their software is so good with all these variables and different features that even if you're wearing a hat, or you just worked out, or you put your hair in a different way, or you're making different faces, is that it can still recognize and consider you and classify you and match you to a different picture of you. So we've gotten pretty far and pretty advanced with our facial recognition software, and it's kind of scary to think how good it is, but it's only probably going to get better. And so on the right, we have a picture of basically somebody's picture of a document. So this has been really useful, for example, in the banking industry and the financial industry. Is I don't know how many of you have gotten a written check and you didn't want to go to the bank and you had an app on your phone. So right now what they have is basically online deposit, where you can take a picture of the check and then that's it. It basically already, just from the picture of the check, and you know people's handwritings these days, everybody's handwriting is different, and there's different positions on the check, and you could take the check at different positions, different lighting. And so the support vector machines can basically look at the check and kind of differentiate and classify, okay, where's the date part on the check, where's the signature. And so for example, in this picture, it can basically, kind of like a grid, it can kind of separate different data points. And in this picture, if you can see, is that there's actually some overlap of the numbers in 1925, but our software is good enough that we can distinguish between the numbers, letters, and etc. And yeah, it's pretty crazy. Like I know some people that have terrible handwriting. Like I don't know if you've ever seen a doctor sign something or those prescriptions and their signature is just a bunch of lines, and our software is still able to detect that and differentiate different letters.
So if we were to take this back to the discussion of logistic regression, and you were saying how the hyperplane is determined by how many different features we have. So when you apply this to images, whether it's the face stuff or the handwriting, I'm sure one thing that really helps is having variation in your training data set in what the images look like. But also, like, what is the equivalent to the number of features when it comes to images? Is it the resolution, how many pixels you have in the image?
Well, for example, I mean, it depend on the data set you're working, right? So, for example, here with the faces, right, it's kind of easier for you to think of different features as just different aspects of um, the face, right? The eyes, distance, and the computer basically trying to locate those. And then obviously for a face is that all of those variables and features have a certain relationship between each other. So for example, you know, if you know where the eyes are, then the computer can kind of guess and locate where the ears are. In terms of like the document, in terms of the pixels, is that yes, to a certain extent, whenever we take a picture or something like that, the actual data of the picture is transmitted in pixels, right? So you have a document where basically all the pixels are assigned or have a certain coloration. So in terms of writing the support vector machines, we're not really going deep into the actual like pixels, but rather we're trying to work with the classification. So for example, if you look at this picture with the 1925, our software isn't going pixel by pixel and then trying to picture what it is, but rather it's trying to take a somewhat a view kind of or perspective that's a bit far back and doing, which is what support vector machines do, is that they classify it, right? So you see those like red squares around the numbers, is that it's basically able to classify a group of data together. And depending on like you were talking about the features. So if I'm taking a picture of a check, certain features could be, first of all, you gotta find out where the check is actually in the picture. And so, for example, like whenever you take a picture of your check, usually they have you like align the check to a certain position to the camera. Or what they do sometimes, like PNC, is that you just take it and then it automatically is able to classify where the check is. And the way they do that is that they typically ask you to take the picture over a dark surface or a contrasting color. And so it makes it easier for the software and the support vector machines to kind of distinguish the shape of a rectangle or a trapezoid shape. But yes, a lot of that in terms of like the coloration, if something is all the same color, I can't really pick out different parts about that, right? So on here, it's a white paper with black text. It's like, yes, because they are different pixels, that lets us classify and distinguish different parts of it. But that's not a necessary part, and it's kind of that's like a more elementary approach in terms of examining what the data is or what the picture is. It's the same thing whenever you code. You're not trying to think about it or trying to express your code in binary, right? We're not really think of it as like 1 zeros, 1 zeros. And same case here is that we already have pre-built code and pre-built software that examines the fundamental like pixels and stuff like that. And what we do on our end is we write the support vector machines, we write the software that takes that information that the computer does already.
Gotcha. Thank you.
All right, so we're not going to go too in depth here, but here's a code example for a support vector machine. So for example, it's going to ask to perform binary classification using nonlinear SVC with RBF kernel. That we're not really going to go into that. You guys, I don't know if you guys ever even heard about that. So for example, let's just look at the color map on the left. So as you can see is that data sets can be very complicated. And if you just remove the different coloration and the lines, you probably wouldn't be able to, with your eyes, distinguish that there's actually different groups in this data. It would just look like a bunch of dots everywhere. There's no really distinct, clear classification. But by using our software, is that the software is basically able to go through many iterations and compare different data sets in record, like very small amounts of time. And that's really the main reason why we do this in software, is that it can do stuff that it would take us as humans long amounts of time. And so you would end up, the result of your classification is you kind of get this hourglass function around your blue data points. And then you get your, basically like two different classifications. I don't necessarily know what data set this is trying to represent, but I'd be really curious to find out what this is. And you'd be surprised is that most of our data in the real world has a really weird scatter plot and no clear correlation. So this is like most of the data that you're going to work with is probably going to have not a real clear classification. If you remember the examples we did earlier where there were two completely separate groups, if you ever get that, then like that's like a dream come true. You know, you're blessed to have that. But you know, because we have the ability to use software and, for example, use SVM with Scikit, it's not the end of the world. Okay, so what are the pros and cons? So basically, at the end of the day, whenever we decide how we're going to classify certain data sets or what we're going to do with certain data, is that we usually make our decision based off pros and cons. Usually, in any decision we make in the world, we want to, if the pros outweigh the cons, then we're probably going to use that. So in the pros, it works well with a clear margin of separation, and it's effective in high dimensional spaces. For example, whenever we have a lot of different features. And the cons, it doesn't perform with large data sets. For example, with faces, if I take, for example, there's 7 billion people on this planet. If I put in 7 billion different pictures and faces, then there's going to be such a large mix of variables that there's going to be almost no distinction at all. And so that's why we kind of want to limit and not take too large of data sets, is that, you know, if you take so much data that you just get a full square just filled with data, then that doesn't really help you. And that's not really the purpose of it. If you remember, in just a lot of these classifications and models and statistics in general, the whole point is that you don't want to work with data that is like representative of the full population. The whole point of statistics and all these models is that we can take a representative smaller sample size to kind of represent the whole population. For example, you know, if we want to figure out how many people like chicken, you know, we can probably take, if we take a representative sample size of maybe like 100,000 people, then assuming it's representative, then without having to go with the effort, the time and resources and the computation of 7 billion, we can kind of predict that it's going to be almost the same. Okay, so the last thing we're going to talk about today is decision trees. This is a lot more simpler than the other ones. Anybody quickly want to tell me what a decision tree is? Okay, anybody want to tell me what a tree is?
bunch of nodes that lead to other nodes.
Exactly. I mean, if we think of just a tree, it has a stump or a root. It's just like one thing. And then as it grows, it starts branching out. And that's typically what, if you ever hear about binary tree, decision tree, or anything, it's modeled actually after like real trees, is that you start from one thing and then you branch off into multiple things. And so if we have something called a decision tree, then as I get more options, my options are probably going to be decisions. So the quick overview. So non-parametric supervised learning. So the goal is to create a model that predicts the value of a target variable following certain decision rules. For example, in somebody's, for example, in somebody's life, we can, for example, we can predict they're going to be an athlete depending on the decisions that they make throughout their life. For example, let's say if I practice every day basketball, I practice, I go to the gym, and I make those decisions. Then my likelihood of me becoming an athlete in college or professionally is probably different than somebody that makes different decisions. For example, eating potato chips and watching TV. Inherently, I think that's a very easy example, but there's a pretty distinct difference in probability depending on which decisions somebody goes through. So decision tree, so each internal node represents a test on feature. So each leaf node represents a class label. So basically node, this refers to the blocks or circles that you typically see in any tree. And in this case, let's continue with that. So here we have a diagram of a simple decision tree. So at the very top, like I said, a tree always branches off from one thing. So here, what we call is, for example, let's say the outlook or the weather forecast, and then we can really branch out to three things. Typically, like in this case, is that we can split it into more things, but the main part or the reason why we use decision trees or trees in general is that we can simplify and get a really broad overview. So for example, it can be sunny, overcast, or rain. And then those branch out to different aspects of the weather. So yeah, every decision tree is going to look different. You're gonna have different amount of branches, different amount of nodes. So this is like the rough outline. If your decision tree looks different, that doesn't mean it's wrong. Almost every decision tree is different. So yeah, that was pretty much everything for today. Here are the external references that I'm going to post. So the main thing that we're going to end up going later whenever we go more into the software is the Scikit library that we use with Python that is used for like the regressions, the support vector machines, and the classification. Basically, if you want to do any of this and you want to use it in your code, you're basically you would be stupid not to use a library that's already pre-built and pre-coded. It has a lot of great features, and depending on what type of project you're doing, what type of data set, the website, it basically outlines the different types of parameters that you could have and different functions that you can use. So the main takeaway from today is that we went over logistic regression, we went over support vector machines or some types of classification, and then we quickly went over decision trees. So quick recap, so logistic regression, we basically use that. It's to kind of predict a binary outcome. So the range of the output's going to be between 0 and 1, which is basically the percentage or decimal that gives you the probability. The support vector machines, overall, that was basically a way to classify or differentiate clusters or groups of data. More so is that one, we can do that with a linear line, or with more complicated groups, we can do that non-linearly, as we looked at one where we used a circle function. So we looked at the ways we can use that in the real world, for example, with facial recognition software, which is probably the easiest example. And we went into basically just the pros and cons and when you should use that. And then last week, the decision tree, we quickly just went over, and anything that you do project-wise, code-wise, anything that deals with decisions, it literally takes 5-10 minutes, sometimes more, to create a quick decision tree of maybe how you want to progress or how the probability is going to be different based on decisions. So next week, we're going to go a bit more into using support vector machines, and we're going to have a little project for you guys to complete. So yeah, anybody have any questions about what we went over today, or just questions in general? Zero questions.
I do have a question, but it's not really related to this, so I'll make sure everyone else doesn't have questions. Yeah.
Gotcha. All right, I mean, no one's asking questions, so go ahead, Bill.
Yeah, so for someone who's pretty experienced with the algorithms we're talking about, and I was wondering if you guys host like larger projects.
Yes, so for example, so one, we have corporate
Mhm.
projects. So typically we do this later, later in the semester or spring semester, where we basically have a project that we work with a company. For example, in the past, we've done stuff with like nonprofits and cocoa packs where we were asked to basically create a website and create a tool for them dealing with their data. And so typically with those, that's more so, it's not like it's not a thing that everybody gets to take part in. So that would be something that we pick and select a certain group of students for those types of projects. So that's one thing, is those corporate projects. The second is that we're planning on partnering and doing some workshops with the developer student club, or the Google Developer Club. So I believe sometime next week, we're gonna have our first collaborations with them. And so we're gonna basically have a workshop where the first half, NDL is going to go into theory and just talk about in general the workshop, and then the Google Developer Club, they're going to take over, and then you guys are going to have an opportunity to kind of be hands-on. And so those are our two main sources of projects, is like the corporate projects, and then projects that we get and we do with a collaboration with other clubs. And I would say if you feel really confident and you want to pursue this and you want to do more, then like it wouldn't hurt if you want to just like reach out or email me. I'd be happy to get back to you and then give you some different opportunities and different things. And in general,
No, yeah, thank you. I was actually on the Cocoa Packs project, and I really enjoyed working with people there. So I was just
sweet.
looking for more opportunities like this.
Yeah, I mean, we're constantly trying to find more projects and find more opportunities for you guys to work on. Obviously because of the online, because of COVID and everything,
Yeah.
it's slightly harder because we don't get like we don't really meet all together in person, and so it's harder for like
No, I understand. Thank you very much, though. I'll definitely shoot you an email later.
but yeah, I mean, we'll try to update you guys all the time in emails and stuff like that in terms of what opportunities and what meetings that we do have. And if you guys ever hear about something that you're interested in, whether it's like you saw something online, you know, don't be shy to reach out and maybe ask, you know, would it be possible if we can look over this topic? You know, I'm really interested in Amazon AWS or how Google does this, because we're trying to make our what we talk about and what projects we do as adaptable as we can, because at the end of the day, we don't want to do projects and go over topics that you guys don't have an interest with and will never use. The whole point of this stuff is that it's stuff that you're going to end up using, and it's going to be attractive for you as an applicant. You know, if you're looking for internships, or you're talking at an interview, or you already have a position, it's going to make you a more effective person in the work environment, and it's just going to make you a better candidate for those positions. Because some of the stuff, especially stuff that's not covered in classes, that's a main topic that we want to go into. All right.
And actually, Bill, I wanted to just use, sorry, I didn't mean to cut you off, Ivan. I just wanted to ask Bill, you know, just since you brought it up, you know, what kind of opportunities are you most interested in? You know, whether it be like, excuse me, like corporate projects or research opportunities, even like shorter stuff like capstone competitions with companies. What are the kind of things that interest you most? So again, ultimately, we can supply that.
Yeah, thank you. So currently so in my research, I research in the BMB department, and we use like deep learning algorithms to find transcription factor binding sites. But I'm more interested in like machine learning in more corporate environments, I guess. But I just enjoy doing projects with people, because currently the project, it's mostly just me working on it. And like in NDL, I feel like the people, of course, are really great, and I just want to have the opportunity to work on meaningful projects with them.
Gotcha. Okay. Yeah, that sounds good. I appreciate that.
Thank you.
I guess I wanted to share one quick update as well before we, not that, you know, if anybody else has any questions or comments or anything, I'll be hanging out to talk. But before people start dropping off, wanted to let everybody know that next weekend we will be having Yu Ong come out to talk to everybody. He's actually a founding member of Nittany Data Labs. He was a senior when I was a freshman. And he did a lot of undergraduate research while he was at Penn State, graduated with a data science degree out of IST, and is now a corporate researcher with IBM. So he is just a wildly brilliant data scientist working on cutting edge stuff, and has a lot of insights into, you know, what should you be doing while you're at Penn State to expedite your career, you know, actions that